Okay, so actually I made the mistake of forgetting to record yesterday's lecture. So I'm just going to go back and briefly go over what we talked about. And that was looking at the initial value problem, solving dy dt is equal to f of t and y. I actually solved the first order linear ODE problem here.
Yeah.
Okay. Then I went on to do explain separable differential equations, homogeneous differential equations, autonomous differential equations, and nonlinear. And so I also showed what to do if we had a second order equation and how to change it into a system of first order equations.
Okay.
And then began our topic of Euler's method, which is what we are currently working on. And with Euler's method, you're solving again, dy dt is equal to f of t and y. And the basic idea is you are given a value of y at a point A, and then in increments of time, small increments of time, we utilize Euler's method in order to create the next iterate. And so we use the Taylor series to derive it. And then I explained the algorithm. I actually solved one problem with y prime equal e to the t. And look at the error estimate was not the best. Then we went on to talk about the actual algorithm for programming it. Then we talked about the error in Euler's method. We did a graphical interpretation, and we had just gotten to the point where we were going to do another example.
Okay.
Okay. So where we are now is we are looking at okay, so here's my example. This one is a separable differential equation. So we have y prime, which is dy dt, is equal to negative t over y. Okay, and I tell you that y at 0 is equal to 1. Okay. Now, the problem with this one is the exact solution to this problem is y of t turns out to be the square root. And if you guys have trouble trying to solve this, just let me know. We can go back and do this. I'm not sure why this is not working for me right now. This is plenty frustrating. Let me try tightening my pen. Okay, so let's see if that helps. Nope, it did not help. Okay, so y of t turns out to be 1 minus t squared. Okay, and so Euler's method is going to produce erroneous results when t is greater than 1. So Euler's method will produce erroneous results when t is greater than 1. Okay, hang on 1 second. I'm getting an error. Okay, so clearly when t gets to 1, this solution, this differential equation doesn't even have a solution after t is equal to 1. So Euler's method is going to produce something that doesn't make any sense. Okay, so before you use the method and you just go hog wild with your delta t or your h and you try to get a solution, you need to make sure that you're even calculating a solution that exists and is unique. Okay, so we'll talk a little bit about that. All right, here's another example. And in this one, y prime is equal to t minus 1 times y to the 1/3 power. And this is y at 0 is equal to y naught. Okay, so the solution to this is y at t is going to equal t minus 1 cubed over 3 plus y naught to the 2/3 power minus 1/3, all of that raised to the 3/2 power. So that's the solution. Okay, so let's say y naught. So if y naught is equal to 1/4, then we get y of t is equal to the same thing that we just had, t minus 1 cubed over 3 plus 1/4 to the 2/3 power minus 1/3 to the 3/2 power. And this is well-behaved. Euler's function is fine. So Euler's method is fine. Okay. If y naught is equal to 3 to the negative 3/2 power, then you get y of t is equal to t minus 3. Nope, that's t minus 1 cubed over 3 to the 3/2 power. Okay, so you can compute using Euler's method until t is approximately equal to 1. Then it blows up. And you should be saying, I don't understand. Why does it blow up? It looks like when t is equal to 1, y is 0. Okay, so why? So up until t is 1, it's fine. Okay, because y equal to 0 is another solution to the problem. So if you see over here, if I had put y equal to 0 is another solution to the problem. Okay, so y equal to 0 is another solution to the problem. All right, so when t goes to 1, y goes to 0, and the solution is not unique. So you need to make sure that your solution exists and is unique. So the main point of this okay, so you need to examine the existence and uniqueness of the solution prior to calculation. So prior to solving the ODE numerically. Okay, so all right, so let's talk a little bit about existence, uniqueness, and stability theory. So where am I? I actually am at 5. Okay, it's telling me I don't have any more applications to close. What else do you want me to close? I only have Zoom and this. Let me just make sure. Instability theory. Now, when you took an undergraduate course in ODEs, I am hopeful that they talked about this topic, so this is not new to you. Okay, so we have dy dt is equal to f of t and y, and we have y at some t naught is equal to some y naught. Okay, so here's the definition. All right. So let y and t be an element of a set D. D is convex. If for T1, Y1, and T2, Y2 that are both in D, then any vertical line segment joining them is also in D. And I think you may have seen this before. So I can draw a really cool circle If it'll let me, no, it won't. But this, here's 1 point. Here's another point. So this is T1, Y1, T2, Y2. Whereas something like this is not convex. Okay. So A, uniqueness. So theorem 1, let f of t and y be a continuous function of y and t, of t and y, for all t and y that are element of a domain D. And then we want to let t naught, y naught be an interior point of D. And then we want to assume that f of t and y satisfies the Lipschitz condition which is as follows. The absolute value of f of t and y, t1 y minus f, I'm sorry, this should be f of t y1 minus f of t y2 is less than or equal to sum k times the absolute value of y1 minus y2 for all y, for all t y1 and t y2, an element of D. And this happens for some k naught, some k. All right. Then for a suitably chosen interval, I, which is going to be t naught minus alpha and T naught plus alpha, there exists a unique y of t solution on the interval I, satisfying dy dt is equal to f of t and y. All right, so we're getting a little deep here. We're doing some theory. Okay. All right, theorem 2. Suppose f of t and y is defined on a convex set D. If there exists a capital M greater than 0 such that the absolute value of the partial of f with respect to y at t and y is less than or equal to m for all t, y in D, then f of t and y satisfies a Lipschitz condition on D in the variable y. And this thing M is going to be our Lipschitz constant. Okay, so that looks pretty good to me. Basically, the solution, I'll have a unique solution if f is Lipschitz, but if I can show that the partial f with respect to y is bounded, then f is Lipschitz, but by the previous theorem, that means it has a unique solution. Well, that looks good to me. Okay, so how does this work? So let's look at dy dt is equal to y times the cosine of t. And we're on the interval 0 less than or equal to t less than or equal to 1. Okay, so I give you y at 0 is equal to 1. Okay, so now the exact solution or the analytic solution is y of t is equal to e to the sine of t. Okay, so the partial of f with respect to y is just cosine t. And so that says that the partial of f take the absolute value of the partial of f with respect to y, and cosine t, so that is equal to the absolute value of cosine t. And we all know that that thing is less than or equal to 1. So that implies that y of t has a unique solution. Okay. Let's go back to the other one. Example 2. I now have dy dt is negative t over y. And we said this was for t greater than 0. And we gave y at 0 equaled 1. And we knew that we got an exact solution. That y was equal to the square root of 1 minus t squared. All right, so now let's go back and look at the Lipschitz condition. So we have the partial of f with respect to y is equal to t over y squared. Okay, now the absolute value of t over y squared less than or equal to m. Well, that implies then that t has to be less than or equal to m times y squared. Okay. But if you remember, eventually y goes to 0. So therefore, t times some number has to be less than 0. So the solution does not exist. For all y. All right. So therefore, we can't even assume that we can't say that the solution is unique. So cannot use theory to show the solution is unique. And if you remember, that case failed. Okay, here's the other one. This is example 1. This is example 2. And this is example 3. And that was dy dt was equal to t minus 1 y to the 1/3 power, where we had y of 0 equal y naught. So we get the partial of f with respect to y. Oh, well, that's the absolute value of 1/3. Yes.
For example 2, since the solution does not exist, it implies that it's unique, right?
No. So we have to be able to show, in layman's words, you must be able to show the partial of f with respect to y is bounded.
Okay.
That's what we need to show. So in this one, the partial of f with respect to y was the absolute value of the cosine of t. Cosine goes between -1 and 1, it's bounded.
Okay, yeah.
In this one, we have the partial f with respect to y, we'll take the derivative, you get minus t over y squared times minus 1. So that just becomes t over y squared. So when you look at the absolute value and you try to force it to be less than some number m, that means t has to always be less than whatever y squared is.
Mm-hmm.
The problem is, look at the actual solution of the problem. Eventually, y goes to 0. So the t cannot be less than 0.
Okay.
So the solution does not exist for all y, meaning we can't find a solution for all y that will satisfy this Lipschitz condition, well, this boundary condition. So now we can't say that it doesn't have a solution, but we can't use theory to show the solution is unique.
Okay. Yes.
Okay, so now in this one, I take the partial with respect to y, and I get y to the negative 2/3. And now I need to force this to be less than or equal to some number m. So that says the absolute value of t minus 1 divided by 3y to the 2/3 has to be less than or equal to m. Okay, so once again, I'm forcing t minus 1 to be less than or equal to 2/3 y to the 2/3.
Mm-hmm.
And this is not necessarily true. So this is not unique.
Okay.
For y going to 0. Okay, so as y goes to 0, you have a problem. Okay, so that's what's going to get us uniqueness. Okay. All right. So let's look at stability. Okay, so now stability says, let's suppose we take the initial value problem and we perturb it just a little tiny bit. Does our solution change just by a little tiny bit, or does our solution change drastically? Okay, so what we want to do is we want to examine the stability of the solution y of t when the initial value problem is changed by a small amount. Okay, so here's a definition. All right. So the initial value problem dy dt equal to f of t and y on the interval a less than or equal to t less than or equal to b, where y at a is equal to alpha, is said to be a well-posed problem if the following are true. 1, a unique solution y of t to the problem exists. And 2, for any epsilon greater than 0, there exists a positive constant k with the property that whenever the absolute value of epsilon naught is less than epsilon and the absolute value of delta of t is less than epsilon, a unique solution z of t to the perturbed problem dz dt equal to f of t and z plus delta of t, again, a less than or equal to t less than or equal to b, but now the initial condition changes just by a little bit. So we can write this as f of t of z of t and epsilon, f of t uh-oh, it's acting crazy for a minute. Don't know why it does this, but it's acting crazy. F of t and z of t and epsilon. And then we have z of f of a is equal to alpha plus epsilon naught. Okay, so now what's happening here? Let me explain. Oh, let me finish the statement that this thing exists. Calm back. Thank you. With the absolute value of z of t minus y of t is less than or equal to k times epsilon for all a less than or equal to t less than or equal to b. Okay, so what are we doing? We start with a differential equation. dy dt is equal to f of t and y, with an initial condition, y of a is alpha. Then we perturb it just a little bit, and we need to make sure that when we perturb it, two things happen. The first, the perturbed solution, which is the perturbed problem, which is this, has a unique solution. And then the difference between the two solutions can be no bigger than some constant times epsilon. Okay, so the main idea is that if small changes are made in the differential equation, or in the initial value, then the solution will change by only a small amount. Okay. All right, so we already have our initial problem. Our initial problem is the initial IVP. So here's the initial IVP. All right. So there's the initial value problem. Here's the perturbed problem. Okay, so we have two solutions, two problems. So now I want to let's let u equals z minus y be approximately epsilon. Well, dz dt minus dy dt, all right, that is equal to f of t and z of t and epsilon minus what I would get for y, which is f of t and y. Okay, so now this piece, whoop, my t's not crossed. Okay, so this piece is du dt. And this piece is f of t and y plus u. Okay, because z is y plus u. Okay, does everybody see that? Minus f of t and y. So now I have du dt, so this is a differential equation. On the right-hand side, it's a function of t and y plus u minus f of t and y. So the partial of f with respect to y is approximately f of t and y plus u minus f of t and y all over u. Think about the definition of how we define a partial derivative. Only thing that's missing is the limit as u goes to 0. So what's missing is the limit as u goes to 0. So that is the partial of f with respect to y. So therefore, f of t and y plus u minus f of t and y is approximately the partial of f with respect to y times u. All right, so therefore we can write that the partial of u with respect to t is that, why do I feel like I have du dt and not partial? I feel like that should have been, nope, that's right. That's right, that's right, it was partial. So the partial of u with respect to t is approximately the partial of f with respect to y times u. So let's integrate both sides. So I'm going to get, this is basically du dt, du over u. So I'm going to get the partial of u over u is approximately the partial of f with respect to y, the partial with respect to t. So when I integrate both sides, I get u is a constant e to the integral from a to t of the partial of f with respect to y, partial with respect to t. All right, u at a is just the constant, it's just approximately the constant. These are approximate. Put an a in there, I just get the constant. But that is z of a minus y at a. And that is equal to alpha plus epsilon naught minus alpha, which equals epsilon naught. So therefore we get u is approximately epsilon naught e to the integral from a to t of the partial of f with respect to y, partial t. So what does that mean? That means for a problem to be well conditioned, we want the partial with respect to y to be negative, because we don't want this to grow. We do not want you to grow. If U grows, that means the distance between Y and Z gets bigger. Okay. Then U will remain bounded by epsilon as T increases. Okay, here's an example. Dy dt is equal to 100y minus 101 e to the negative t. Y at 0 equals 1. So this thing has solution y of t is equal to e to the negative t. All right, so here's the perturbed problem. So the perturbed problem is dz dt is equal to 100y, 100, that's got to be a z. See you later. Minus 101 e to the minus t. But now I want z of 0 to be 1 plus epsilon. And the solution to this problem is z of t is equal to e to the negative t plus epsilon e to the 100t. All right, now that's a problem because this term right here this term rapidly departs from the solution. Okay. And if we look, the partial of f with respect to y is equal to 100, not well conditioned. So even though the original problem gave us a very nice stable solution, e to the negative t dies out beautifully. This one has the part that dies off, but it has a very bad growing part that came from just by making this like 1.01. That little change causes the solution to grow up. Okay, so here's the main idea. And that is the original problem must be well conditioned for the numerical problem to be well conditioned. Okay. Okay. That was 6 with stability. Okay, example. dy dt is equal to 1 over 1 plus t squared plus, I'm sorry, minus two y squared. So the thing on the right is f of t and y. And then I give you y at 0. So there's the problem. Okay. The solution, the exact solution or analytic solution, is that y of t is equal to t over 1 plus t squared. So that's a really pretty solution. Okay, 1. Is the analytic solution unique? How can I determine if the analytic solution is unique? What do I need to do? Okay, any ideas?
So check if it satisfies the Lipschitz function.
Okay,
Yes.
very good. That's exactly what my notes say. Check Lipschitz. Okay, so we need to know that the absolute value of the partial of f with respect to y is less than or equal to some m. Okay, so the partial of f with respect to y, forget the absolute value for a moment, that's just negative 4y. Okay, so is the partial of f with respect to y, which equals the absolute value of negative 4y, less than or equal to some m. So that means we need to maximize this, make this as big as it possible for all y. If we take the derivative again, we'll see that the biggest this thing can be is 4. Okay? The biggest it can be is 4. So yes. All right. Okay. Is the analytic solution stable? Okay, well, we need to check. See that the partial of f with respect to y is less than or equal to 0. And we get the partial of f with respect to y is equal to negative 4y. And is that less than or equal to 0? Well, we know y, if y is greater than 0, which it is, so that checks. All right, so therefore we can go on and solve the problem. And the numerical solution with the error is yi plus 1 is going to equal yi plus f of ti yi plus O of h squared. That's my error. Okay. And note that order H is the accumulated error. Okay, global error. This was... Okay, global error. You say, why do you care so much about error? Because I'm trying to solve a serious problem. I need to make sure that I don't have too much error, because my error is what's going to mess me up. Okay, now what I'm going to cover right now, the undergraduate students are not required to know in detail. Okay, because this is actually way deeper than 431, but it's required for 661. Okay, lemma. Okay, for any real x or t, 1 plus x is less than or equal to e to the x. We all know that. And for any x that is greater than or equal to -1, we can say that 0 is less than 1 plus x to the m is less than or equal to e to the mx. Okay, so we can say that that limit is true. It's easy to prove. The Taylor series for the exponential, the first two terms are 1 plus x squared over 2 plus x cubed over 6, blah, blah, blah. And so if we just truncate it at 1 plus x, it's definitely less than the exponential. Okay, so the proof of this is just Taylor series. That's very easy. Okay, so I'm going to use this. So now I have a theorem. So let's assume that the analytical solution, y bar of x of the initial value problem dy bar dx of f of x and y bar of x naught is equal to y bar naught. That thing is Lipschitz. So the absolute value of f of x and ya minus f of x and yb is less than or equal to, I think I called it k, but it turns out that it's just the same thing, m of ya minus yb. So m is the Lipschitz constant again. We're going to assume that this whole solution has a bounded second derivative. On the interval x naught b. Okay. Then the solution obtained by Euler's method that is yn plus 1 equal to yn plus f of xn yn for n equal to 0, 1, 2, etc. satisfies the max over all x naught less than or equal to x less than or equal to b of the absolute value. Okay, stop. of the absolute value of y bar at xn minus yn. So the m solution at any time is less than or equal to e to the b minus x naught times capital M minus 1, that whole thing over M over 2, the absolute value of y bar double prime in the infinity norm. That thing is less than or equal to C times H. Now I gotta remember what C is. Okay, this is the global error. Okay, so as I struggle to remember what C is, we will pick up here on Tuesday. Now, you will notice that I gave you guys another homework instead of an exam because one, you hadn't had an opportunity to try problems on that on the material that we worked on. So I decided to give you homework. And I kind of like doing the homeworks instead of the exams. I think y'all, the big exams are not necessary. So I have to figure out how I'm going to finish out the course, whether I'm going to give you a final exam or a final project. So I'm going to think about that and see what we do. Okay.
Okay. So the exam for tomorrow.
Nope, there's no